Right. Good morning, my dear students. Right. In this session, we will talk about the step 5 calculation uh, in case of portal method. We are solving for laterally loaded building frames by an approximate method called portal method. So till the last sessions, we have completed four steps. Okay, stepwise we are calculating. So let's see what we have in step 5. Okay, so I'm sharing the content. Right, this picture is from the last session I brought in. So as you observe, we have completed 4 steps, and you can visualize that the step 1 answer is here. Step 2, like column shear, column end moment, and then beam end moment. Step 3, then step 4. Okay, right. Now let's talk about last step in calculation of column axial load. How you calculate column axial load. So the only quantity left for calculation, right? So it is by vertical equilibrium of free body diagrams formed by the assumed hinges. Uh, so you have to take free body diagrams. I'll tell you in a simple way. So you have applied assumption 1. So the initial step of solving the problem. So we have applied step 1. So with that assumption. So before that you have applied assumption 1. So each member has got one hinge at the middle. So zero bending moment, right? So where you can separate the entire frame into so many pieces, so those you take now. Okay, so like let's see. So this is the top most corner. So let's see this one. So there is a hinge here, there is a hinge here. So this part you can separate it. Okay, so likewise, so you have a hinge here, you have a hinge here, you can separate this part. Same way, you have a hinge here, you have a hinge there, you have a hinge here. So just separate this T-shaped diagram. This is like inverted L-shaped diagrams, and between you have T-shaped diagrams. So all these are free body diagrams. So how they help you? They help you to calculate column axial load, because you see that you have separated the part of a beam, part of a column, right? You agree? Right. So this point, at this point, you have separated the part of a structure from the whole structure. So you have internal forces there. What are all there? So there is a hinge, so bending moment is 0. and this is a beam, so you expect only bending moment and shear. So already shear is calculated, you have a value, so 6.667, and here it is a column that there will be three internal forces. Anyhow, bending moment is 0 because it is a hinge. So one shear and axial load. Shear is already calculated. Okay, so what will be the value there? It's there is no point in knowing that, you know the value, but anyhow it is not needed, not required here. Reason what? You want this value, right? So like f ah column ah. So if you want this vertical force, so we will be applying sigma f y is equal to 0. Means what? There is no need of representing horizontal forces because you don't take them into this equation. You take only all vertical forces, sum is equal to 0. Got it? So by taking free body diagrams formed by, how you got those free body diagrams? Formed by the assumed hinges. Okay, step 1, I mean to say assumption 1. Okay, so your assumption 1 has given you the free body diagram, so many free body diagrams. So pick each free body diagram, represent only vertical forces. Beam vertical force means shear, column vertical force means axial load. For a beam, vertical force means what? It is a shear force. For a column, vertical force means what? Axial load. Okay, so that's how it is, right? So this is the same represented here, right? So you know this value, right? Direction, you don't know this direction, so we are assuming it. So if you get a positive value, you maintain that. If you get a negative value, just reverse it, that's it. So that will tell you whether it is tension or compression, that's all. Okay, right. So this is how we proceed. Okay, so VAB, shear force, you know this direction and force both are known to you. And next, you assume this direction, and you don't know the value of column axial load. So right, so upward force plus, if it is written, this will be minus, you are writing FAH is equal to 0. So FAH is equal to VAB. That means FAH is a positive value. Means what? Your assumed direction is correct. See, you compare the diagram that I have drawn. You see, I have drawn like this 6.667, and I have mentioned that here I have an upward force. I assume like this. Just let us say, what happens? I apply sigma Fy 0. So FAH, I take upward force as positive, plus 6.667 is equal to 0. What you get? FAH is equal to, just a second, some extra line. So FAH is equal to minus 6.667. What happened? You got a negative value. Means what? The direction here is not okay. you have to reverse it. That's it. The same you are getting. So just by the observation, you can put the arrow in a guessed manner. So you can guess it easily. Here you have an upward force for shear. So to balance that, there should be a downward arrow. Okay, that's much simple. So either you guess it in a correct manner, or you just take some direction, it will automatically be corrected by the equation. If you get a positive value, you keep the same direction. If you have a negative value, just reverse it. That's it. Okay, so that's how we proceed. Right, so this is the leftmost no free body diagram. Similarly, the rightmost free body diagram you have like this. So both are downward here, right? So upward forces positive, if you say minus VCD and minus FDE is equal to 0. So maintain these notations even when you solve on your own the problem. So V is given for shear, F is given for axial load. Okay, right. So FDE is equal to minus VCD. So VCD value is 5, so it is minus 5. Hence, I mentioned this as upward. Though I assumed it as downward, I mentioned this as upward. Got it? That's how you have to solve this. So next, free body diagrams. I said giant B. The free body diagram uh, of the portion consisting of joint B, and free body diagram of portion consisting of joint C. Likewise, you take joint wise attached free body diagram. That's simple for you to notate. Okay, so let's see joint B attached free body diagram. So to the left you have one shear force, to the right you have another shear force. Okay, be careful. You see, right, this is the joint B you are taking, and you are considering this portion of beam. So what you have here, you have a downward shear. What you have here, upward shear. That you should take it to your diagram. You see, downward, upward. Okay, so the value and the direction you must bring it as it is from the earlier solution. Okay, do not commit any mistake at this point, right? Axial load is your wish. Either you assume it as downward or upward, doesn't matter, because it will be corrected automatically when you solve it. Okay, so taking some direction as positive, say upward positive, here I have taken upward positive, let us say. So VAB is downward, so minus we write, and VBC upward we write plus, then again this is downward we write minus. So we want this value, so it is positive, means what, this direction is correct. Okay, so likewise, so whatever it is, if you get a positive value, your assumed direction is correct. If you get a negative value, your assumed direction is wrong, and you have to reverse that. So let's see giant C, how it is in the diagram. Right, this is giant C. Let's clear that to have a clear picture of it. Right, so now you are taking free body diagram of this the portion attached to the joint C. So where you have to split, this is where you have to split. Right, this is perfect. Now you have to draw as it is there without this arrow. You don't want this one because it is horizontal force. You want only vertical force. So we represent some direction, either upward or downward for axial load. That's it. This you have to add there. Other things are same. Say 10 downward here, 5 upward here. Okay. So this is 5 upward, 10 downward. That the same thing you have to bring it to this diagram. Let's see here. This is downward 10, upward 5. Got it. So this is assumed. This direction is assumed downward. So downward 10 means minus 10, upward 5 is taken as plus 5. So finally you are getting minus 5 as your value. So this arrow should be upward. That is mentioned here. So FCF means what? Axial load of the column CF is no upward. Okay, that's how it is, right? So this is how you follow the procedure. So this is for the topmost joints consisting of so many free body diagrams. Likewise, you have to proceed for all other the diagrams. Okay, let's see what next. So E and H. Okay, so E joint E associated free body diagram is taken. So let's see what it is in the diagram. This one, joint T associated free body diagram. So this one, so where you have one beam and two columns. So where you know this value now, this axial load is calculated for this. Okay, so you know this value, either upward or downward, you know this value. And downward 12.5 is already known. So what you need is this one, this value. This you have to calculate. Okay. So that's how it is. So it's very simple if you understand that. So just by taking free body diagrams, in between these points of contraflexures, so associated with a particular joint. Okay, so bring that members connected to that joint. Right, let us see what you have there. So right, so FED, FEL and VEF. So all these values you substitute whatever you have earlier calculated. So FED, the axial load in column ED is already known to you, and EL is to be calculated, and EF is already known to you, beam shear. So that is 12.5. So finally 17.5 upward is the axial load. Okay, so this direction is to be reversed. Same way H, you have to consider H, joint H. So where that H is leftmost joint, we have gone for this joint. Same way, take this part of invert rotated T joint. This is like T rotated. Okay, so 16.667 upward force here, and the axial load from the earlier calculation. AH, you have value for AH. So you have axial load AH 6.667. Okay. And I'll make it clear how you take that AH value. So see, you have this column and you have that part of the column. This is A, this is H, where you have beam extended, and another portion of the column. Right, got it. Now you see that this value of axial load here that you calculated, you see that it is downward 6.667. Let's see that. Here it is downward. You have solved this one, 6.667. So for this part of the column, that is upper half of the column, this is lower half of the column, right? So for this, how your axial load should be? So for this one, it should be like this. Because when you join those two portions of column, half of the column above, half of the column below, when you join both the columns, the force should become 0. So that's why this is upward arrow. 6 value same, 6.67. So that's why you see FHA how I represented upward arrow, right? It's very typical. You have to be careful with this, right? So you have solved the upper joint. You got a value in axial load, value of axial load and the direction. But when you take the connected joint, say column AH, okay. So H is the joint. So joint A, joint H. So joint A you solved, and you have taken half of the column, and considering joint H, so you are now looking at below the half of the column, bottom one, not the top one. So the axial load, that the direction of the axial load, what is fixed for the upper part of the column is not same. It is to be reversed. That is what is done here. Okay. So this is very much essential. You have to practice this one very much. Got it? Right. So that's why it is this arrow is upward mentioned here. And you don't know this value and you have to calculate this one. And anyhow, this is well known. Direction is already there in the solution of beam shear. So that's how this has to be calculated. So FHI 23.334 positive means the direction is okay, downward. This is how you have to uh, proceed for this one, right? So the other two joints, now they are middle joints, so you will get four members joining, two beams and two columns. Let's see G and F. Let's see joint G how it is. This is joint G. Okay. So 16.667 downward force, 25 upward force, two shears. Okay. Right. There are two columns, BG column and GJ column. Already joint B you solved and you know axial load in BG. Let's see what is that. So this is this one. You see BG downward force of 3.33 when you have taken joint B. Okay, now you are taking the below joint, so 3.33 downward force. I'll make it little more clear. So this is column BG column. Okay, right. So this is uh, say, downward 3.333. So how you should apply now? Upward 3.333. This is B, this is G. So when you consider joint G, you should represent it as upward arrow. Let us see how it is done. Now you see upward arrow for BG. Okay. So shears you don't need to worry. Only column axial loads, how you take them when you change the joint, that is more. Okay, right. So this how you are no, following it. Okay, so uh, I don't know how far you are getting that. Okay, so let's go back to the PowerPoint. Right, so that's how the BG direction is brought in from the earlier calculation. Same way for all other joints also. Okay, so you have to find GJ value, that is 11.667 downward. Okay, same here. Say when you are talking about joint G, this is downward. When you go for J joint below 1, then this will become upward arrow. That simple it is. Okay, so you have to always represent that. Once you finish your solution, then it will be very easy, right? Giant F in a similar manner, you have to practice. That's it. That's the only way you get clarity, and with no ambiguity you can easily work out for that. So this is downward arrow that you assumed, but it is it should be reversed upward. Okay, right. So then the bottom joints like I, L, okay, all that. So this joint I, joint L, very similar. J, K. So with that, no, your step 5 will become completed. So I, L, I'm not no going for that because it is very similar procedure. You have to work out no, on your own. Just practice this one. How you brought in IH, how you brought in LE, the directions and the values. So IP you should calculate the here, and LM you should calculate here. So these are the axial loads, where LM direction is opposite. Similarly, the other joints J and K. Okay, right. So where 4 members are there. So again, this, as I said, GJ we talked just now. So there it was downward. Now when you go to joint J, means this is the joint J, the arrow should be upward. This is what I was telling. right? So jo required the value, all other three values are known to you, so jo value. Similarly kn, okay, and this is upward value. The downward direction that you assumed is not okay. It is from the calculation, right? So proper understanding is required only with respect to axial loads. Shears are already there, okay? So you don't need to worry about them. Right. So now representing all the axial loads. So now you understand with this yellow colored, or I mean to say gold colored arrows are the axial loads. You see, when you take joint A, you got a downward arrow. Okay. Whereas when you take joint H, the same is becoming upward arrow because of equilibrium only. Okay. So when you join those two portions of column, half of AH above and half of AH below, when you join them, uh, the forces should vanish. That is free body diagram concept. Okay, action and reaction. Similarly here, and the arrows you see, which means these two columns are different in nature, axial load, and these two columns are different in nature. Okay, so likewise it maintains the same. Means what? The frame is being pushed towards right hand side. So the left two columns are in tension, the right two columns are in compression. So this is compression. These two columns are in compression, these two columns are in tension. Okay, so this the frame is towards right. Okay, so this face is in compression, this face is in tension. The forces are pushing the frame to the right, is maintained. Okay, so why you are calling this as tension? It's very simple. So for this arrow, for that part of that, how you should have an arrow upward, because this is downward arrow, you should have an upward arrow at this end. Same way, there is an upward arrow here, so there should be a downward arrow. Okay, so now you just look at this as a single member, as a column. What you have now, that is tensile force. That is what I said. So left two columns are in tension, right two columns are in compression. Something like this. Okay, so this is how the entire solution of a frame, you see how big the frame is. Three-storied frame we have taken, and we have completed step-by-step solution and also represented everything in a diagram. This final diagram is the complete solution. All five quantities you see, beam end moment, beam shear, column end moment, column shear, and column axial loads. So all five quantities we have calculated. Okay, but step by step if you follow, and you don't need to worry at all anything. Okay, so very much care is required when you see this, when you calculate step 5 calculation, where the axial loads are to be brought in from one joint to the other joint. So you need to be careful with the directions that you apply. Okay, so this completes the analysis of a frame applied by lateral loads for by portal frame method. Okay, one of the approximate methods. Okay, so you practice the problems uh, from the earlier question papers or else from any textbook that you follow, and practice in this manner. Let it be whatever procedure you have uh, in your textbook, whatever you follow, right? You practice in this way. Let's see how simple the solution is, right? Thank you.